Morning, boys and girls. Welcome to another lesson on Technical Sciences, grade 12. I hope that you are feeling well and you had a good day at school, and those that have already started, they have started with CAT, Computer Applications Technology. So our final examination matriculants has officially started. So I hope that chances are you are not doing CAT and you are using all this time to prepare for all your subjects, and that includes technical sciences. So thank you so much for tuning in. We are continuing with our topic, which is light, and we know by now that this topic forms part of paper 2, and it carries a lot of marks, which I will tell you about later on, just towards the end of the lesson. So I hope you are ready for me. You have your pens ready, you have your notebook ready, and we are starting. The overview of the lesson structure is that we are going to first look at what you are required to know in terms of light as per the examination guidelines. And then in the features of the topic, we will be learning about light, and we will be doing a question from previous examination papers on light, and as well, I will give you more tips in terms of preparing for this section for your examination, as well as the mark allocation. So my dear learners, let us shoot straight into our lesson. Right, so under light, my dear learners, remember, these are the definitions that you are required to know. You are required to know how to define the term wave. And we've done that in the previous 2 days. And we simply said it's a disturbance that transfers energy through matter or space. So this is a wave, so it will transfer energy, and it can be in traveling in matter, rather through matter, or in a vacuum space, meaning in a space that does not contain any matter. Again, you are required to know the definition of reflection. And we definitely know that it is the change in direction of a wave upon striking the interface between two materials. Remember what I said to you. I said to you, when we give a definition for reflection, you must actually tell us what is it and how does it happen. So it is the change in direction of a wave, and that is upon striking the interface between two materials. So we know by now what reflection is. It's not really the focus of the day. And then you must know how to define the term refraction. And we know it is the bending of light when it passes from one medium to another. My writing's a bit skewed there. Right, I'm just underlining the keywords there for you. When it passes from one medium to another. So know this, if you look at the definition of reflection as well as refraction, you should be able to see that we basically explain what that reflection and refraction is, and when does it happen, or what causes it to happen. So the full definition must have that, because I have seen in a couple of times when we mark you, a learner would just say it is the change in direction of a wave. You can't just say that. It is the change in direction of a wave upon striking the interface between two materials, and then it is the bending of light when it passes from one medium to another. Then you are required to know how to define the term critical angle. And we discussed this. We said it is the angle of incidence in the denser medium such that the refracted ray just passes through the surface of separation of the two media. So you need to know this, my dear learners. It is an angle of incidence, you will remember that, and it will be in the denser medium. And the ray which is refracted is going to be on the surface of separation of the two media, which is what we have talked about in the previous days. What you don't see here that we've talked about is the laws of reflection and the laws of refraction. And you know you must be able to state them. And it's 2 laws for reflection and 2 laws for refraction. And we know that by now. So we are not really revising that. Perhaps when we do questions, we will revert back to that. Then the focus for today is going to be on dispersion, which is defined as the phenomenon whereby light breaks up into its component colors. So you can take white light, or what we refer to as visible light. And this visible light, when it is shown or when it shines on a prism, or when it strikes a prism, the light rays, they can definitely be dispersed. So the light can disperse, it can break up into its component colors, which are the 7 colors that we know: the red, the orange, yellow, green, blue, indigo, and violet. So dispersion is the phenomenon whereby light breaks up into its component colors. And we will understand further how does that happen. Then we talked about the laws of reflection and the laws of refraction. We've already discussed that. And total internal reflection as well, we discussed that. And that is when the angle of incidence is greater than the critical angle. The ray of light reflects into the original medium. You will remember that if you see that the angle of incidence, you are increasing it and it eventually becomes bigger than the critical angle, the light ray, instead of undergoing refraction, it will then undergo reflection. And we recall that total internal reflection. And why is it reflection? Because it reflects into the original medium. And we must be able again to discuss conditions of total internal reflection. And we know those conditions, we have 2 of them. And just a quick review is to say the angle of incidence must be greater than the critical angle. Then you will have total internal reflection. Secondly, the light must be coming from a more optically dense medium to a less optically dense medium. And I said to you, we will ask you these questions. And then we said you must be able to state the uses of total internal reflecting prisms. And I indicated to you there that you must know 2 uses. At most, we'll ask you for 2. And one that I gave you is that it is used in endoscopes. And another one is that it is used in optical fibers. So know that. So all of this we have talked about. Perhaps in terms of the loss of reflection and the loss of refraction, maybe I must just give you that refresher again, my dear learners. Remember, you will state 2 points here, the two laws that goes with reflection. Number one, we know the law must talk about the relationship between the angle of incidence and the angle of reflection. Secondly, the other law must then talk about the incident ray, the reflected ray, and the normal. So we go. Let us start with the first one. In terms of the laws of reflection. The law of reflection tells us that the angle of incidence is equal to the angle of reflection. We get a mark. Secondly, the law of reflection tells us the incident ray, the normal, and the reflected ray all lie in the same plane. That is the second mark altogether. Then we have the laws of refraction. In the laws of refraction, number one, it must also talk about the relationship between the angle of incidence and the angle of refraction. And then it has to talk about the normal, the incident ray, and the refracted ray. So let's start then. What does it say? It says, this law of refraction, there is a relationship between the angle of incidence and the angle of refraction when the light ray passes through the boundary between the two media. Secondly, it says the incident ray, the normal, and the refracted ray all lie on the same plane. So just a refresher there. Now, the second focus for today is going to be on lenses. Now, remember what I said to you. The first one, we are going to focus on dispersion. Secondly, we are going to focus on lenses. Then, under lenses, we must be able to discuss the frequency and wavelength of the various components of light. Then we must be able to discuss and draw the transmission of light through convex and concave lenses. And we must be able to discuss the application of convex and concave lenses. And lastly, we must be able to give the properties of images formed by concave and convex lenses altogether. So we must be able to talk about that. Now, again there, my dear learners, we must be able to talk about the properties of both the concave lens itself and a convex lens. We must be able to give those properties. Are we clear, my dear learners? So we are not only going to look at the properties of images, we must also look at the properties of the lenses themselves, because we ask you these questions and learners think that if they know the properties of the images, that's enough. You must know the properties of the lenses themselves altogether. So please take note that, because I know that a lot of you are using these examination guidelines in order to answer questions. Now, let us go to the dispersion of light. And we say dispersion of light is the phenomenon whereby white light breaks up into its component colors. That definition is always going to be asked, and it will be for 2 marks. Nothing other than that. We won't give you 1 out of 2, it's 2 or a 0. And all the keywords are important there, and they must be in the correct context. It must be indicating that light is being broken up into its component colors altogether. Now, what else must we know? We know that the higher the frequency, the lower the wavelength. Now, when white light breaks up into its component colors, it breaks up into 7 colors, which we will discuss. But amongst those colors, we have violet. And another color of the 7 colors, it's red. So it's a red color. Sometimes we call it violet light or red light. So in these lessons, my dear learners, rather in these 7 colors that white light breaks up into, we have violet and we also have red. Now, violet, my dear learners, is just next to ultraviolet, and red is just next to infrared. So our memory serves us well that violet will then have a higher frequency, which means it will have a lower wavelength. And then it tells me that red light will have a lower frequency, so it will have a longer wavelength. And that is why there I say higher frequency, lower wavelength is that of violet light. And therefore, it will travel slower through glass than the lower frequency or higher wavelength, which is red light. In other words, because violet light has a higher frequency but a lower wavelength, then it travels slowly in glass. And red light has a lower frequency and a longer wavelength, so it travels faster. And because of this, violet light being slowed down to a greater extent because it travels slowly in glass, it then refracts more than, excuse me, because it travels slowly inside glass, then it refracts more than the red light. So this is what happens, my dear learners, in terms of refraction. Upon entry of white light at the first boundary of a triangular prism, right? My surface today is not so smooth and the pen isn't moving as smoothly. So when it moves through a triangular prism, meaning it goes from A to a triangular prism, there will be a slight separation of white light into the component colors of the spectrum. So when white light comes from A and it goes into a triangular prism, the white light is going to break up into its component colors. And when it breaks up into its component colors, we say dispersion is taking place. But at the first boundary, when it immediately strikes the white light, rather when it strikes the triangular prism, you will then find that the light partially separates into its component colors. But when it exits the triangular prism, meaning at the second boundary, then the white light breaks up even more into its component colors. And that is when the 7 colors are clearly visible. And the diagram below will show you that. Are we together? Right. Now, this is exactly what we are talking about when we talk about dispersion. Now, there we have white light. It is coming from air, and this is your triangular prism. Now, when your light ray, this is white light, it's coming from air and it is going into this triangular prism. You see there at the boundary, my dear learners, the white light starts to break up into its component colors, but not completely. And the colors are not as visible and as separated as we would want them to be. But there at the second boundary, the white light completely breaks down into its component colors. And that is what we refer to as dispersion. Are we together? This is what we refer to as dispersion. So we see that the white light, when it came, it was white in color. And now it partially breaks down into its component colors. And there at the second boundary, it completely breaks down into its component colors. And this is what we refer to as dispersion, a phenomenon whereby white light breaks up into its component colors altogether. And we can see there, one color is red, another color there is violet. This is violet. And this one is red. Are we together? Right. And this red is refracted less. We can see that. Refracted less. And the violet is refracted more. And the violet is refracted more. Are we together? So why is violet refracted more? Because it has a high frequency so it has a shorter wavelength, and we know the symbol for wavelength is that, and therefore the speed is less. And the opposite is true for a red color. It is refracted less because it has a lower frequency and a longer wavelength, and the speed is more. So please know about that. Are we together? Right. So that is dispersion. Let us move to lenses. And with lenses, we are going to look at a convex lens as well as a concave lens. Firstly, This is how a convex lens look. Now, when you look at a convex lens, you can see, look at the middle. The middle is thicker altogether than the edges. So the middle is thicker than the edges altogether. So this is a property of a convex lens. It is thicker at the center than at the edges. So this is what you must be able to see. So this is the structure of a convex lens. Again, we say it is converging in nature, and we will explain that. You see, when you have a convex lens, and these are light rays that are passing through a convex lens, my dear learners. These light rays are going to converge. Basically, they are going to meet, and they will meet at that point, which we call the focal point. So a convex lens will take the light rays, and they are going to converge, and they will meet at the focal point. So this is converging, and that is why we say a convex lens is converging in nature, because it makes the light rays to meet up, and they meet up there at the focal point. So these are properties of a convex lens altogether. And these convex lenses, my dear learners, we know about convex lenses. And these convex lenses, they are used by people in so many instances, like the glasses that we wear. Now, when you go to an optometrist and they check your eyesight and they realize that you are farsighted altogether, you have a condition, an eye condition that we call farsightedness, then your lenses are going to be made up of a convex lens, because a convex lens is going to correct that eye condition of farsightedness. So when you have a problem, an eye condition that we call farsightedness, to fix that, or for the optometrist to fix that, then they must give you glasses that are made up of convex lenses. And that condition, farsightedness, it's also called hyperopia, or it is also called hypermetropia. That is farsightedness. So when you have a condition of farsightedness, to correct that eye condition so that you can see clearly everything, then your lenses are going to be made up of a convex lens. Then, this is what I was telling you. The rays of light that pass through the convex lens are brought closer together, so they converge. So a convex lens is a converging lens. Then, when parallel rays of light pass through a convex lens, the refracted rays converge at one point called the focal point. So all those rays that are moving parallel to what we call the principal axis, which you will learn about when we continue with lenses, you will then realize that all those rays that were moving parallel will pass through the focal point. Remember, there will be rays that are coming from the object and through the optical center. Those ones, they don't change direction, so they will not be going to the focal point. But those that are parallel to the principal axis, they will move they will be refracted to the focal point. So they will converge there. And then we know the distance between the focal point and the optical center of the lens is called the focal length. So if this is your optical center, the center of the lens there, and that is the focal point, the distance from this point to that point, we refer to that as the focal length. Altogether, there it's actually shown. So the focal length is the distance there from the optical center to the focal point, and we refer to that as the focal length. Good. So that is that about convex lenses. Now we will be required to draw the path of a light ray, the image that is formed when light rays move through a convex lens, which is what we'll do tomorrow when we go deeper into lenses. Then let us look at a concave lens. These are the properties of a concave lens. Now, firstly, if you look at the concave lens, you can see it is thin in the middle than at the edges altogether, which is the exact opposite of a convex lens. Because a convex lens, you will remember, it is thicker in the middle than the edges. But now we're talking a concave lens. It is thin in the middle than at the edges. That's a mark. It is diverging in nature. So the light rays do not meet altogether. The light rays do not meet. They diverge. They move in different directions. And we can see that there are the light rays, they are diverging altogether. They do not meet at the focal point, unlike these ones. These ones are converging, they are meeting at the focal point. In a concave lens, they are diverging, they do not meet at the focal point. Remember, what you are seeing there is not the light rays, is just an extension. So the light rays do not meet at the focal point. So diverges, it doesn't converge, it is diverging in nature. And my dear learners, we will ask you these properties. And remember, these properties of a concave lens and a convex lens, it's actually what makes these lenses to be different. So if I also asked you the differences between a convex lens and a concave lens, you can actually give the different properties of a convex lens with that of a concave lens. But when you give the differences, my dear learners, obviously you must compare similar items. So I can't say a convex lens is thicker in the middle than the edges and say the difference is it is diverging in nature. No, if I talk about a convex lens is thicker at the center than the edges, then the difference will be a concave lens is thinner in the middle than at the edges. So those must be aligned because you're comparing similar things. The other difference is that a convex lens is converging in nature. So which difference goes with that? Is that a concave lens is diverging in nature. Now, you must know the properties of an image formed by a concave lens. Now, this is a concave lens. You must know this will always be the case. Always be the case. So we want to know how the image of a concave lens is going to be. And we say the image is smaller than the object, and it will always be smaller than the object. So the image that is formed through a concave lens will always be smaller than the object, the image will always be upright. In other words, it will be erect. It will be like you see the object. It will be upright. And the image is visual. Why are we saying it is visual? We can ask you this. Because the light rays do not meet. A visual image is an image that is formed because the light rays formed when the light rays do not meet. So it is visual. The light rays do not meet. And hence we said it is diverging in nature because the light rays do not meet. So those are the three properties of an image that is formed by a concave lens. Then the application of a concave lens. We're talking a concave lens. So a concave lens corrects an eye condition that we call myopia. When we talk about myopia, we are talking about short-sightedness. We are talking about short-sightedness. So if you have a condition, an eye condition that we call myopia, or an eye condition that we call short-sightedness, then we will make, or the optometrist will make your lens to be from a concave lens altogether. Right, and that short-sightedness condition, we call it myopia. Sometimes, because we say short, we simply call it nearsightedness. It is the same thing altogether. So you must know that. Always remember, a convex lens corrects farsightedness, which is hypermetropia, which is hyperopia. Concave lens corrects short-sightedness, or what we call nearsightedness, or what we call myopia. So remember that. So tomorrow the focus will then be on actually drawing the path of these light rays through a convex lens and a concave lens, so that we can study the images that are formed by drawing. Now, the uses of lenses, please remember that we use it in microscopes, in your medical eye glasses, in your magnifying glasses, your binoculars, your telescopes, your projectors, as well as cell phone cameras, because they're able to zoom and magnify and everything. So those are generic uses of lenses. So that really brings us to the end of the main theory for today. And we have actually sort of done 98% of the work, except that tomorrow we will be literally drawing the images that are going to be formed. Now, let us do a question. And this question encompasses what we have learned for the week. The diagrams given below, A and B, show two phenomena that can take place when a ray of light strikes a glass prism. Study the ray diagrams and answer the questions that follow. Here I have diagram A. I see there is a light ray coming in. So this is the incident ray, right? This is the incident ray. And then they've shown me my normal. Remember, the normal must be perpendicular to the surface, so it is perpendicular. So this angle then, between the normal and the incident ray, we call it the angle of incidence. Now, after the light ray enters this glass prism, we can see it is going in that direction, it goes in that direction, it goes in that direction, it goes in that direction. So what is happening in here? After it goes into this direction, it continues in the same medium altogether. When I see a continuation of a light ray in the same medium, I know that I am talking about total internal reflection, because this light ray keeps on reflecting in the original medium, right? It's not a once-off reflection, so it's repeated reflection. So we are talking about total internal reflection. Are we together? Then in diagram B, I see my incident ray, the one that strikes the surface. And then I also see my angle of incidence because it is between the normal and the incident ray. And then I see the ray that is being refracted. So that we know it is the refracted ray. Why? Because the light bent. Okay, the light was bending when it was entering the second medium. So that is refracted ray. And the angle there will be the angle of refraction. And I can see the refracted ray is bending towards the normal because I'm moving from, chances are this is air and this is glass. So if I move from air to glass, I'm moving from a medium of low optical density to glass, which has a high optical density. So the light ray will bend towards the normal. The speed will also decrease when it moves into the glass. And then I have the ray that emerges. And we know that ray, we call it the emergent ray. It emerges on the other side. And then this angle between the normal and the emergent ray, we call it the angle of emergence. And what else can I learn here? I know that the angle of incidence is definitely equal to the angle of emergence. So I've analyzed my diagram. Then when I do questions, it's very easy. We are required to define the term reflection. And we know reflection is the change in direction of a wave upon striking the interface between two materials. There it is. The change in direction of the wave upon striking the interface between two materials. We know this, and that is going to be 2 marks. All the keywords must be there in the correct context. And then we must write down the name of ray X. We've talked about this. It is the ray that strikes the surface. So we said it is the incident ray. And then ray R. What is happening here? Total internal reflection. So now I have reflection because the light is reflecting into the original medium. So it must be reflected ray because we're talking total internal reflection. So that will be the reflected ray. And then ray R No, ray Y is the one that emerges on the other side, and we said it is the emergent ray. And then the angle that is labeled theta in diagram B. So theta in diagram B is the angle between the incident ray and the normal. So it is the angle of incidence. We've already discussed this. You see, when you analyze your diagram, when you get to the questions, it's very easy. And then the phenomenon taking place inside the prism in diagram A, we've talked about this. We said the light is continuing to reflect in the original medium. So we are talking about total internal reflection. Good. Total internal reflection. There we go. Good one. The phenomenon shown in diagram B. In diagram B, definitely, my dear learners, I have refraction. You see, I have the incident ray, the refracted ray towards the normal, and the emergent ray. So the light bends towards the normal, and then from glass to a bends away from the normal. So the bending of light, we know, my dear learners, it is refraction. Then we continue. 7.3, state two requirements for the phenomenon taking place inside the prism in diagram A. So we want to know what are the requirements for total internal reflection, because that is the phenomenon in diagram A. We know this, my dear learners, right? In order for total internal reflection to take place, the light ray must be coming from it must be from a more optically dense medium. It must be from a more optically dense medium to a less optically dense medium, which is class 2A. So it must be to a less dense medium. Secondly, we know for total internal reflection, the angle of incidence must be greater than the critical angle. Must be greater than the critical angle. Remember, my dear learners, the critical angle gives you that refraction where the light passes through the surface of separation between the two media. So if you increase even further, the more it goes away from the normal. So you are now giving an angle of incidence that is greater than the critical angle. Then they say, is ray Z refracted away or towards the normal as it travels inside the prism? Give a reason for the answer. So there are two parts. We first have to tell if Z is going away or towards the normal. After that, we give a reason. We start. Ray Z right. Ray Z Okay, away from the normal as it travels inside the prism. So ray Z is the incident ray. So when it goes into this prism, it will go towards the normal. And we have discussed this, my dear learners, because it will be coming from air, which is less optically dense, to glass. This ray Z is coming from air to glass. So it's coming from a less optically dense medium to a more optically dense medium. So it will bend towards the normal. So our answer there will be towards the normal. And we know the reason. Ray Z moves from a less dense medium. So the first mark is for towards the normal. The second mark is that ray Z moves from a less dense medium. So from a less dense medium, that's one mark, to a more dense medium. And that will then give you the third mark. Or another learner could have said it, the ray Z comes from a medium of lower refractive index to a medium of higher refractive index. Then the last question says, how does the angle theta in diagram B compare in size to the angle alpha, looks like alpha, in diagram A? Right, only larger than, smaller than, or equal to. So we want to see how theta compares to alpha. Now, alpha is definitely a greater angle altogether. It is definitely a greater angle than alpha because it is an angle that is causing total internal reflection. And the angle that causes total internal reflection, my dear learners, an angle that causes total internal reflection, it's an angle of incidence that is even greater than the critical angle. And therefore, it tells me this one doesn't even cause that. So angle alpha, it must definitely be greater than. So angle theta is smaller than angle alpha. And we must be able to explain the answer. This is because alpha is a greater angle of incidence because it causes total internal reflection. Altogether. So one mark for there is for smaller than, and then the other 2 marks is for the statement there. And that is a total of 16 marks. And we have done all of this, my dear learners. So I really, really hope that you will get ready for your questions for paper 2 on light, because really we got a good sense of the type of questions that they will ask us. In terms of light, remember it is plus minus 41 marks. So I'm really hoping that you will get all the marks, in fact, or as many marks as possible. And we will be continuing with this topic tomorrow as well as Friday. And we will be looking at lenses more and get more questions. And then we are well on our way to getting our level 7s. So Send me questions to stemdigitalschool@africateengeeks.co.za so that during our question and answer session, I will be able to help you with any questions of your choice. Thank you for tuning in and enjoy the rest of the evening. Goodbye.